Hello everyone, welcome to my structural analysis tutorial section. I'm Cheng Ning. Today I'm going to talk about how to draw shear force diagram. Alright, I will talk about the rules, okay. Of course, in a beam, okay, I mean if there is a beam like this, okay, if you cut an arbitrary point, okay, you will find that in this point, okay, there is axial force, shear force, and bending moment. I will talk about how to draw axial force and bending moment in the later videos, but I will start with shear force first. Let me remind you, okay, if the shear force is like this, okay, upwards at the right face, we call this positive shear force. And then, if this is a downward at the right face, we call this negative shear force. Okay, what I mean is that, let's say I tell you that VB is 10 kilonewton. Okay, what I mean is that, okay, let's say negative 10 kilonewton. It means that, okay, at point B, if you cut this point, the shear force is negative. It means that at the left side is upwards and at the right side is downward. Okay, so this is negative. This is negative 10. Okay, the magnitude is 10. The direction is like this. Okay, it's like this. All right. So then I'm going to talk about. Of course, I want to focus on how to draw a shear force quickly. Okay, rule number 1. If okay, there is no loading between 2 points, let's say A and B, it means that, okay, VB is equals to VA. Let's prove this, okay. Let's say you cut these 2 points. If there's no transverse loading, there's no downward or upward force or distributed force transverse to the beam, there's no change of shear force. I mean is that if you cut A and B, okay, of course you will find a pair of shear force. Let's assume that VA and VB are all positive. For VA, I call VA positive means that the right face, okay, at the right face the arrow is upwards, okay, and at the left face the arrow is downward. So this is VA, VB. Of course, we also have bending moment, okay, bending moment like this, but this doesn't matter. From the force equilibrium along the transverse direction, VB is equal to VA. Right? So this is pretty simple. Rule number 2. If there is a concentrated force, okay, acting between point A and point B, okay, let's see what will happen. What I'm interested is the point just at the left of point B and the point just at the right of point P, the force P, okay. You know that from A to A prime, okay, this is A prime, okay, there is no loading, okay, transverse loading, so VA prime is equal to VA, and VB prime, similarly, VB prime is equal to VB. So what will happen at this very small region? This is P, and then this is VA, okay, because VA prime is equal to VA, right, and then this is VB, okay. So at this very small region, the very small, say dx, very small region dx, okay. We know that, okay, of course we have axial force and bending moment, but that doesn't matter. Okay, from the summation of Fy equal to 0, we know that, okay, VA equals to P plus VB, or equivalently, VB minus VA is equal to negative P. The change of shear is negative, okay, negative. Alright, the change of shear from the right to left, okay, if you walk from this direction, okay, the difference between the shear at the right side and the left side is P. Whether this is positive or negative depends on the direction of the arrow. If this force is push you down, okay, push you down, it is negative sign, okay, negative, okay, negative sign. If the force is push you up, okay, push you up, then it's positive, okay. That means that if this is P is like this, okay, delta V will be equals to positive P. Alright? Rule number three. Number three is like this. If you have a very crazy distributed loop between 2 points, let's say something like this, omega x, then point A and point B. Okay, what will happen if you cut this two this segment out? Okay, you have a loading like this. Okay, and this is called omega x, and then shear force VA and VB. Of course, you have axial force and bending moment, but that doesn't matter. And let's say this distance is okay. Let's talk about the distance first. From here, from the first equilibrium, we know that VB, okay, is equal to VA plus the sum of these little arrows. Okay, in mathematics, it means that the integration of omega x from A to B. Okay, what means that the change of shear is simply the area under the loading. Okay. Again, how do we decide whether this is a positive or negative change? Depends on the arrow. If the arrow is pushing upward, then this is a positive changes. Okay, the changes will be positive. If this is what to say, a downwards, it means that the changes is negative. Okay, from here we know that. Okay, from here we know that if the changes is very small, if you divide both sides by dx, okay, this will approximate to omega x. When delta x approach to 0, okay, what means that the change of shear force is actually the loading. Okay, we can easily derive these things. Okay, suppose that, okay, if you cut 2 points, these 2 points are very small point. Okay, okay, let me derive this to you. Okay, suppose that you have a very small region, and you call this v of x, and then this one is a v of x plus dx. And then you have a loading upward at a very small region, which you can consider is as constant for sufficiently small region. From the fourth equilibrium, you know that, okay, v of x plus dx is equal to vx plus omega x times dx. Okay, the total loads due to this little uniform wx. So from here to here, you know that vx plus dx minus vx divided by the dx is equal to omega x. When this length dx sufficiently small, approach to 0, then dx become derivative. Okay, dx dv by dx equals to omega x. Okay, so what I mean is that when you draw the shear force diagram, okay, the slope of shear force diagram actually is the distributed load. Alright? Okay. Let's try to do some example. Suppose that, okay, let's see how can we quickly draw the shear force diagram. Let's say okay, let's say, okay, this is load, and then we draw some crazy shear force here, okay, and then like this. Okay, let's say I have some loading. Okay, distributed loading, uniformly distributed, and 5 kilonewton per meter, and then I have a moment here. Okay, 20 kilonewton meter, and then I have a loading pushing upward. Okay, 6 kilonewton, and then let's say let's draw it a bit longer, and then I have a one loading here. Okay, 10 kilonewton. Okay, randomly put some number, and then where's my mouse? Okay, and then let's give some dimension. Here, and let's see. 4 meter, 8 meter, 4 meter, 4 meter, and 4 meter. Alright, first, before we draw the shear force diagram, the first step we need to do is to find the reaction force, okay, to find out the reaction force. So let's say this is called A, B, C, D. Okay, we know that if I cut this point, okay, from the equilibrium of this dy, okay, so this is 10, this is hinge, right? Okay, of course we have some axial force and tension force, and shear force, okay. If I take the moment at this point, we know that this is 20, okay, this is 20. So this is 40 kilonewton total load provided by this distributed load. If you take moment at point A, okay, summation of MA equals to 0, we know that, okay, let's draw some loads first. This is 0, okay, this is BY, okay, you can see that the X for this couple, okay, is 20 minus the moment contributed by this distributed loads, okay, 40 times 4, and then plus by times 8, and then plus 6 times this total distance is 12, yeah, and then minus 10 times this is 20 equal to 0. We also have dy, don't forget about dy, okay, and also plus dy times what's this, 60, okay. So from here we know that by is equals to negative 6.5. Okay, and let me check the number again to guarantee that the answer is correct. Alright, so the answer is correct. So how about AY? AY is pretty simple. From summation f y equal to 0, okay, AY minus 40 plus BY, okay, and then what's this? Plus 6 kilonewton, and then plus dy, okay, and then minus 10 is equal to 0. So, oops, sorry, equal to 0, okay. So AY, by the way, BY is negative number, so you plug in negative number. So the total answer is plus 10 minus 6, and then plus 6.5 minus 20. So AY is simply 30.5 kilometer. So let's see whether this is correct. Okay, it's correct. Okay. Alright, we can start to draw our shear force diagram. Okay, our first shear force diagram example. Okay, sometimes they use S, sometimes they use V, doesn't matter. It depends on the background they have. Alright, let's draw the line first. This is A, and then this is B. So this is a blanket, this is 4 meter. And then this is C, this is a hinge. And then this is D, and then this is the concentrated load, okay, somewhere around here. Okay, we start from this direction, okay, this direction. because at this point do not have any shear force, so the shear force is 0 up to point A based on rule number 1. Remember that in rule number 1, okay, if there is no loading, no transverse loading, then point A, shear force at point A will be equal to shear force at point B, okay? Because the shear force at the beginning, okay, here is 0, okay? So at any point that it will not change. So up to point A is 0, okay? When you reach point A, because we know that point A is has an upward force of 30.5 based on rule number 2, it will have a jump. Okay, the jump is 30.5. Okay, this 30.5 is simply based on rule number 2. Okay, if there is a concentrated force between 2 points, okay, you know the point A is 0. Okay, at the left side of point A, but at the right side of point A, okay, the changes will be the loading at point A. Okay, the loading of point A is pointing upward. Alright, so this is 30.5. And then based on rule number 3, okay, the shear force will reduce, okay, will change, okay, based on the area between 2 points of the under the area of the loading. At this case, it's downward, so it's negative. How much we lost? How much we lost? We lost 40. So we lost 40. So from 30 to 40, we lost about negative 9.5, I think. Okay, negative 9.5. Negative 9.5. Okay, the slope here, according to the slope is 5. Okay, why? Because based on this rule, okay, the slope of the shear force is the if it's this distributed force. In our case, the distributed force is uniform, so it's a constant slope. Alright, let's see, 30.5 minus 40 is 95. When we reach point B, okay, point B is a negative 6.5, which means it has a downward, okay, 6.5. Okay, again, based on rule number 2, okay, we will reduce, okay, further reduce to 6.5, so which means this is negative 16. Between point B and point C, there is no loading, so it's kept constant, remain unchanged, okay, until point C. And then at point C, the loading is upward of 6. So something like this. So this is 10. From point C, from point D, nothing happen. At point D, the loading is upwards 10. Okay. So the loading is upward 10. So after that, this is negative 10. Okay. And then this is 10. And then until at point D, until somewhere around here, still remain constant. Until this point, okay, it's pushed downward to 10. Okay, so this is the shear force diagram of this particular loading condition. Let's write down the equation. Let's see in local axis. Okay, let's say this is x1, and then this is x2, and then this is x3, and then this is x4, and then this is x5. Okay, v of x1 is simply 0 because there is no shear force, and v of x2 is the starting point 30.5. Okay, based on this rule, okay, the integration rules. Okay, here instead of point B, we choose arbitrary point. Okay, v of x. Okay, so any point of x. It is the integration of omega x. So omega is 5. Okay, but it is downward, so it's equal to negative 5 x2. And then vx3 is nothing but what's this, negative 16. Vx4 is negative 10. You can see that from x4 until before x5 is negative 10, and then vx5 is vx5 is 10. Okay, So that's it. Okay, we finished the first example of the shear force diagram. In the next video, I will talk about how to draw axial force and also bending moment as well. Thank you.